Welcome to this explainer of our source material. Today, our mission is to decode the statistics you see every single day, and we're going to do it without getting bogged down in complex math. We're going to pull back the curtain on how data is actually summarized, and sometimes how it's manipulated. Okay, let's dive into this. Here's our roadmap for today's mini masterclass. We'll start by exploring the average trap. Define mean, median, and mode, learn to be aware of the outliers, uncover the secrets of measuring the spread, and finally, look at real-world statistics. We're keeping this highly digestible with a logical flow. Let's get right into it.
Section 1. The average trap.
The premise of the average trap is simple but absolutely critical. Relying on a single number to summarize a massive set of data can be incredibly misleading, which brings us to a really fundamental question. What does average actually mean? When you read a news headline claiming the average home price is skyrocketing or the average worker is doing great, what are they really telling you? We really need to challenge our basic assumptions about the everyday statistics we're constantly fed. Let's imagine you walk into a room with 5 friends. Their ages are 10, 10, 12, 14, and 54. Maybe a very old uncle is visiting. Now, if you calculate the arithmetic average by adding those ages up and dividing by 5, you get 20. But think about that number for a second. An average age of 20 represents literally nobody in that room. It perfectly proves that in everyday language, the word average is dangerously vague.
Section 2. Mean, median, and mode.
These are the big 3, the core tools statisticians use to truly find the center of a data set. First up is the mean. This is your standard arithmetic average. In conversational math terms, you literally just sum up all your values and divide by the total count. It is by far the most common measure of central tendency out there, and it treats every single value as equally important. But, as we just saw with our 54-year-old uncle, treating every value equally has a pretty glaring weakness. Next, we have the median. This one is brilliantly simple. The median is the exact middle value when you arrange all your data points in order. If you literally lined everyone up by age and picked the person standing in the exact middle, boom, that's your median. Because it relies entirely on position rather than arithmetic, it's completely immune to those weird extreme values at the ends of your data. And finally, the mode. The mode is simply the value that appears most frequently. Think of it like a frequency counter. It's absolutely perfect for finding the most popular categorical item. For instance, if you run a retail clothing store, calculating the mean shirt size is totally useless. But the mode tells you exactly which size sells the most, so you know exactly what to keep in your inventory. Now, what's really interesting is how these 3 measures interact within a specific data set, like these 9 student quiz scores. The mode is 7, because it pops up 3 times. The median is also 7, sitting perfectly in the middle position. But the mean, it gets dragged down to 6. Why? Because those surprisingly low scores of 1, 2, and 4 exert a heavy, downward mathematical pull on the mean, while the median and mode remain stubbornly anchored to the typical student's actual experience.
Section 3. Beware of the outliers.
If statistics were a movie, the outlier would for sure be the silent villain, just quietly distorting reality in the background. Picture a typical small company where the employees earn around $30,000 to $34,000 a year. Now imagine the CEO walks into the room and their salary is $500,000. That massive extreme value right there, that's our outlier. Let's actually look at the math on this. Without the CEO, the mean salary of those employees is a very representative $32,000. But the very second you add that single $500,000 salary into the mix, the mean violently jumps up to $110,000. One single extreme number wildly distorted the mean by $78,000. If that company boasts that their average employee makes $110K, well, it's technically true, but completely deceptive. So the crucial point here is, this is exactly why government reports always use the median household income. It protects the truth from the outliers. To summarize, here is a quick breakdown of how outliers stretch the tail of your data in skewed distributions. In right-skewed data, like our salary example we just talked about, the long tail stretches to the right, constantly pulling the sensitive mean higher than the median. In perfectly symmetric normal data, they're all perfectly equal. And in left-skewed data, the tail stretches left, pulling the mean down. The major takeaway? Outliers basically drag the mean around on a leash, while the median stays solidly anchored. Section 4. Measuring the spread.
Knowing the center point is a great start, but to get the full picture, we desperately need to understand the variability, or how spread out the numbers actually are. And this brilliantly illustrates why. Let's compare Company A and Company B. In Company A, everyone earns exactly $100,000. In Company B, the CEO earns $1 million and everyone else earns $10,000. Both companies have the exact same arithmetic mean of $100,000, but the actual real-world experiences for the people involved couldn't be more different. We clearly need a tool to measure that difference.
That tool is the standard deviation, which measures how widely dispersed our data points are from the center. It's actually a highly logical step-by-step process. First, you find the mean. Second, subtract the mean from each score to find the deviation. Third, you square that result, and this step is vital because it stops positive and negative deviations from just canceling each other out to zero. Fourth, you add those squared results together and divide by the number of scores minus 1. Finally, take the square root of all that to get back to your original units. So, why go through all that math? Because of the empirical rule of the normal curve. Standard deviation is basically statistical magic. It tells us that 68% of our data will fall within just one standard deviation of the mean, 95% falls within 2, and a whopping 99.7% falls within 3. For teachers analyzing test scores or analysts looking at manufacturing quality, standard deviation gives a rapid, crystal-clear picture of performance.
Section 5, Real-World Statistics.
We're going to transition to practical application now, proving these aren't just abstract textbook concepts, but highly useful daily tools. Imagine you're analyzing a massive data set in Microsoft Excel. You have 240 NBA basketball players and all of their 2020-2021 season stats. You want to find the center and the spread for age, points per game, and tons of other metrics. Calculating this manually on a notepad? That would be an absolute nightmare.
But in Excel, it literally takes seconds. This is definitely a cheat sheet moment. To find the mean, you just type equals average, followed by your data range. For median, it's equals median. For the mode, it's equals mode.sngl. And for unbiased standard deviation, it's equals stdev.s. And honestly, the best part? Once you type it for one column, you just grab the autofill handle, that little green square in the corner, drag it right across, and you instantly calculate massive data sets across every single category.
Which leaves us with this final provocative thought. You are now officially armed with the data literacy skills to cut right through the noise. So, when you read the next news headline boasting about an average home price or an average economic recovery, will you just take it at face value, or will you ask the absolutely most important question, is that the mean or the median? Keep analyzing, stay curious, and thanks so much for joining me on this explainer of our source material.